Welcome everyone. Thanks for joining our webinar this afternoon on monitoring urban heat from space, exploring emerging satellite technologies. My name is Christy Spire and I'm currently the Nature Stewardship Team Leader here at Green Adelaide. And as you all know, this is our fourth instalment of our seminar series for 2026, which we run to help share the great work happening to make Adelaide cooler, greener, wilder and more climate resilient. And we know that each of you online play your part. So thanks for joining us and being a part of it all. We always like to acknowledge the country that we're meeting on today, and I hope you can take a moment to acknowledge where you are, where you're located, how connected you feel to your country today, to the country that you're on. I'm 4 stories high in a very corporate building, but I'm looking out on the beautiful skies of Kaurna country. Mani ngadlu tampanthi, ngadlu Ghana, yatanga imparenti. That translates from Ghana to we acknowledge that we meet on the land of the Kaurna people, and we acknowledge and respect the connection that they hold with their land, waters and community. And we pay our respects to their elders, past, present and all the ones emerging as well, that many of us have the privilege of working with here and across Adelaide and further afield as well. Always a good moment to stop and ground ourselves. Thank you to Ghana for the privilege of working with you. So today's session is being recorded and will be available on the Green Adelaide YouTube afterwards to watch as well if you lose us halfway through or anything. And you're very welcome to join in the chat at the end. So you don't have access to a mic, but you've got access to a chat so that you can put in your queries, share any feedback and any links that you may want to share with other people online today. So as our cities continue to warm and heat waves become more frequent and intense, understanding where urban heat accumulates and who is most vulnerable to its impacts is becoming increasingly important. Urban heat affects not only our comfort, but also the health and well-being of people, plants and animals across our city. So today we're hearing from presenters from Flinders University and Green Adelaide about a collective project delivered in partnership with the Department for Environment and Water and SmartSat CRC. They'll tell you more about what that means later. Exploring how emerging satellite technologies could transform the way we monitor urban heat across Adelaide. This project builds on the aerial thermal mapping undertaken in 2022 and evaluates the potential for satellite thermal imagery to provide more ongoing and cost-effective urban heat monitoring. The findings could help inform future planning, heatwave response, urban greening initiatives, and community resilience strategies. So lots of opportunities for it to be applied. So I'm pleased to introduce our 3 speakers today that are coordinating themselves across one presentation. Sarah White, our Regional Data Officer with Green Adelaide, David Bruce, Professional Research Fellow in Earth Observation, and Michael Hillman, Research Associate in Earth Observation Data Analysis. So looking forward to you all taking us away for about 40 minutes, and we will have 15 minutes at the end for questions. So I'm handing over to David to start with. Thanks, David.
Good afternoon, everybody. I'm just going to share our presentation. Should be coming up pretty shortly. So let me first of all acknowledge all the people that were involved in this project. Some of the names we've already mentioned. We haven't mentioned James Cameron, James Peters, or Blair Pellegrino thus far. So that's additional to this. And I notice in the lobby and now in the room, I think we had Addie James, who was part of the satellite development process that we had working along. So thank you to all those people. So Fabrice Ma from the SmartSat Cooperative Research Centre was going to do this presentation, but unfortunately he's in Brisbane at the moment, so I'm standing in for him. Hopefully Fabrice is listening if he's got the opportunity. So the project was entitled Kenyini Waru. So we jumped from Ghana to Pitjantjatjara, and of course the translation Kenyini is got various meanings over all kinds of different ways. My understanding from living with Pitjantjatjara people is that it's a connection between land and earth, between earth and the sky. It's an emotional connection which is very deep and probably not in our language. And the word waro we've added to this. Waro is Pitjantjatjara for fire, often hot. So this is something about a Kenyini connection to space and with heat. That's the very loose translation of this. So this project started, I guess, has a legacy back in 2016, and then it grew from there with the Department of Environment and Green Adelaide using aerial imagery, which Sarah's going to talk about, to look at the temperature of our city. There was the suggestion that with the development of the Australian Space Centre and the SmartSat CRC that we could develop our own satellite. And in fact, that's what they did. And they built a satellite called Kenyini. A little bit more about that in a moment, but this presentation is really asking some questions. What do we currently do? How do we measure it? Can satellites replace it? Could South Australia build its own satellite to do this job? How frequently do other satellites measure urban heat? Is it daytime and nighttime? What kind of resolutions can we measure from space? And what can we use these thermal observations for? So let me switch to Sarah, who's going to tell you about what we have done in the past.
Thanks, David. As David mentioned, we've got a really good grounding in aerial thermal imagery capture over Adelaide, started by councils back in 2016 and continued over multiple projects since then. And then Green Adelaide in 2022 undertook a project to capture urban heat tree canopy across the entire region. And as part of that, we really discovered one of the key learnings from that project was the limitations of that aerial thermal imagery. It's great in that it's very high resolution. It's 2 meters resolution, so we can see that really detailed look at different surface types and the impact that's having on its surrounds in terms of land surface temperature. But as you can see here, it's very limited at that regional scale, that you can't compare each capture day. So each of these little areas is a different day of capture. So it's very much limited to the temperature and the conditions at the time of capture. And you can't compare. So prime example here, you can't compare one side of Playford Council to the other side. So that really limits you in terms of any sort of monitoring, any sort of being able to do any change detection. And the third big limitation to aerial thermal imagery, unfortunately, was the cost of it. That, as I said, it's great high resolution imagery, but that financial cost means that we're unable to afford to capture it more than once every 4 to 5 years. So that led to the question of, can satellite imagery provide something comparable or even complementary? But thanks, David. I'll hand back to you.
So something about the Kenyini satellite. This is what we call 6U, which means 6 units. Each unit's 10 centimetre cube. So it's a relatively small satellite, designed, constructed, built in South Australia and launched from California in August 2024. Michael and I actually watched the launch virtually. We actually saw Kenyini come out of the system. It was led by SmartSat CRC, but with South Australian government investment, a number of different stakeholders in that, including University of South Australia and multiple private operators. And on board, we had a thing called Hyperscout 2. It's a hyperspectral sensor, lots of sensing of the spectrum, and a thermal imager, and that's the thing that we were interested in using. It was fully commissioned in 2025 and delivered quite a number of images, 50 or so images, and it was, I think, a landmark achievement for South Australia. Obviously, Australia has launched satellites before, but this is the first one for South Australia. The satellite delivered some thermal imagery. Here's a picture of some thermal imagery over the Adelaide region in early 2025. But unfortunately, there was a technical anomaly, a failure that meant that we couldn't collect or download the imagery after a date, I think in February or March of that year. So unfortunately, we didn't get too many pictures that we could test to validate this. So then the question shifted, so from can uni do this to what can other satellites do? And that's where we spent a lot of our effort looking at all that. But let me go back to Sarah, because she wants to tell you more about urban heat.
Cool. Thanks, David. So bringing it back to why we're doing all of this investigation, I imagine a few people here would have heard a lot about this, but we're basing it on the idea of the urban heat island effect. So it's an effect of cities being hotter than their surrounding natural environments. I read a paper yesterday that Adelaide's been measured as being up to 7 degrees hotter than our surrounding natural environments. So it's all due to that increase in grey infrastructure, grey surfaces such as roads, buildings, artificial surfaces that absorb heat during the day and slowly release it out into the environment at night. So it creates a hotter area and affects people's comfort. So the fact that it's releasing heat well into the night, it affects people's ability to sleep and just general health impacts. And one of the key findings with urban heat island is it's not equal across an entire city. Neighbourhoods in lower socioeconomic areas with less access to green spaces are more likely to be impacted. And so urban heat islands have been observed, amplifying the impacts of climate change and heat waves in cities, and just really having a greater impact. So as I mentioned, areas with low socioeconomic areas are mostly impacted, and most vulnerable people in communities who are already feeling those impacts are the people who are unable to afford to turn on the air conditioning or afford energy efficient housing, or people living with long-term illnesses and or mental health or long-term disabilities are very disproportionately impacted by heat waves. And we see higher levels of mortality related to heat waves. It's one of those things that people don't really see in terms of, we just accept in Australia that it's hot, but people are very severely impacted mentally and physically by heat waves. And the natural environment's feeling the impacts too. I'm sure many people would have heard of a lot of mortality and death rates amongst the grey-headed flying foxes in Botanic Park with heat waves. And just that increase in heat and limited access to water as droughts increase. It's disrupting natural cycles. So as the soil dries up, trees are struggling to grow and thrive. So it's not just people, it's also being impacted on the environment as well. Thanks. So this brings us back to why do trees and green spaces matter? They're known and they've been referred to as nature's air conditioner. So healthy growing vegetation has been observed to cool its surrounding areas through evapotranspiration and shading, and it also provides other benefits such as pollution absorption, carbon capture, and this has been observed to be much more efficient and when it's a biodiverse green space. So we've got a great little summary here that, there has been a lot of observations from multiple cities that in a green city, they can be up to 8 degrees cooler, so offsetting the impacts of that urban heat island effect. Thanks, David.
So back to me. I'm going to tell you a little bit more about how we sense things from space. So thermal energy is predominantly emitted in the sort of 3 to 40 micron part of the spectrum, electromagnetic spectrum. So human beings, we're observing in the 0.4 to 0.8 micron range of the spectrum. So this is way beyond our visual perception. We know it as the thermal infrared. And the little graphic below shows you the significant amount of energy in the visible part of the spectrum, which is a result of reflected sunlight. But over here in the thermal part of the spectrum, in this region between 3 and 40 microns, but particularly around about 10 microns, we see a low amplitude of signal coming from the Earth's surface, which gives rise to some issues when we're trying to sense things. So we've got a small signal there that's occurring through this process. So this means that our detectors, together with the fact that the sensitivity of detectors reduces, means that we see around about 100 to 1,000 times less information in the thermal part of the spectrum than we do in the visible part of the spectrum, which gives rise to the fact that thermal infrared, thermal temperature pixels have to be much bigger to absorb, to get sufficient photons of light to make a significant reading. So that's why the resolution of our thermal pictures are always worse than visible pictures. I point out as well that it doesn't matter which satellite we use, we have to calibrate for the atmosphere, calibrate for the sensor as well, which gives rise to some issues. So some other things about resolutions. As our low Earth orbit satellites orbit the Earth, they have to travel from north to south or south to north at a fairly high speed. And they do this to effectively balance the forces of centrifugal force and gravity, to balance those two to keep the satellite in the sky. So it's whizzing around like this at the same time the Earth is rotating, which means the opportunity to come back and visit the same spot on Earth is constrained somewhat. So what we call our temporal resolution is affected by a number of factors, these orbit types, the mass of the satellite, the speed at which it's traveling, and what we call the image swath width. So ideally, what we'd like to have here is a satellite that whizzes around, gives us a picture of our temperature every 12 hours. That is day and night. That's the ideal solution. The width of the image, the swath width of the image, is controlled by a number of factors, but ideally we want to be able to cover a whole city in one picture as it moves down from north to south. So for Adelaide, that's about 35 kilometres wide, and you'll see how that affects various things as we move along. Right. So if we look at our existing satellites out there, and what I'm going to talk about native resolution, the spatial resolution with which they capture things. Here's a bundle of satellites sitting over here is something you may have heard of before, Landsat. It has a temporal resolution of 8 days because there's 2 satellites in the orbit. That means it takes 8 days for one of these 2 satellites to come back and observe the same spot on Earth. At the same time, its native spatial resolution, that's the horizontal axis, is 100 meters. Each pixel, 100 meters. Popping over here, Sentinel-3 gives fairly good temporal resolution, but poorer spatial resolution, and likewise. What we see in this graphic is the bubble size indicates the swath width. So for Sentinel-3, it's a fairly wide swath width, Landsat a bit less. And we look at Cagnini, which operated for a few months there, is sitting up here with 17 days repeat temporal resolution, but 300 meters as our pixel size. So ideally, oops, let me go back a section. Ideally, what we want is something down in here every 12 hours and really high resolution. And we can see there's a bit of a gap in there. There's a few surrounding this, with one sitting in here called SatView. We'll show you that later. If we look at a thing called reprocessed resolution, this is where suppliers of satellites take the native resolution and improve it by some method. So for example, Landsat, 8-day temporal resolution, gets resampled to 30 meters. So this is an improvement using some techniques. And we see some others in here. Constellar, HydroSat, there's a completely synthetic product in there. Planet have a product working in another part of the spectrum, SatView and Constellar. So these names will pop up. Here's a desired temporal and spatial resolution, and we're not having anything sitting in there particularly well. If we relax those constraints out to the sort of the green circle, we can see that some satellites are potentially useful. All right, I'm going to switch over to Mike, who's going to give us some selected results from some of these satellites.
All right, thank you, David and Sarah. I think that's really informative information about, I guess, the key components here, the satellites that are available, what we can get, and why we want to do that. We want to do urban heat, but we really need to go back a couple of steps and evaluate the instruments that are available and the data that's available to us and understand what that actually looks like. And we can build up our knowledge of our confidence and our understanding of how the different surfaces and how the different parts of Adelaide look under different conditions. So I'll present some data from our field work, from Landsat. David's mentioned Landsat is the absolute workhorse of Earth observation that I'm sure that a lot of you would have heard of. And then a couple of new players, the sort of this thermal space, like all satellite spaces, are becoming increasingly attractive for commercial interests. And HydroSat and Constellar are two companies that we've negotiated with and got some data from. There are more, and that this space will be rapidly expanding and developing as we speak, certainly over the next few years. So just reference our area of interest is Adelaide. We're getting data from satellites. What does it look like, and where are we headed with this? David, if you give me that one click again. I'm going to talk about this a lot, so I'm just introducing it now. This is our logical spatial unit. It's a mesh block. It's the Australian Bureau of Statistics' smallest spatial unit that they use and then publish as part of their census and demographic analysis. The good thing about mesh blocks is that they are geared towards a single land use. So they're not really highly specific, but they are in that sort of range of useful to us because we can separate out certain land uses. So we come back to this mesh block. You'll hear me say that a lot. This is what a mesh block looks like. If you can decode that image on screen, it's the Adelaide in the central part, it's the Adelaide CBD, and the pale blocks around the Adelaide CBD, or the empty blocks, are the parklands. We can see North Adelaide, and then we can see some of the roads and houses, etc. So we'll see this kind of pattern a lot. If we go to the next slide, please, David. So I said we did some field work. We need to understand what a satellite observation of the Earth looks like while we're actually standing on the Earth under the satellite. So we went out to the field a number of times in a number of different locations as the various satellites were coming over. Some of those satellites are very easy to predict. Landsat has a very well-known predictable orbit. The commercial satellites, there are other complicated factors. So those satellites are going around in orbit all the time, as David pointed out, but they're not necessarily capturing everything all of the time. They have commercial interests, so there's other factors at play. Anyway, whenever we knew there was a satellite of interest coming over and it was a clear sky day, we went out to the field and we gathered some results. Overall, it's complicated, but overall, it was a very positive experience, and we learned about how the different surfaces interact and how that might look when we combine them in however we're going to use this data. So we're thinking about, we're not interested in pixels really. We want to get back to that logical spatial unit. We want to make something meaningful because we're headed towards what Sarah was describing as urban heat islands. So that's a whole lot of analysis. If we go one more click, please, David. It's just a very simple example of what I'm talking about. We had a hot reference site and a cool reference site. On this particular day, 19th of Feb, Landsat, it was a hot day. we sampled both of those sites and we aggregated the data up to that mesh block level, and we just compared it to what the satellite told us. We can see that we're within around 2 degrees. So the hot site was less than 1 degree and the cool site was 2 degrees, different than what our ground measurements and the satellite said. Actually, we're very happy with that. It's well within the error margin. It's well within the uncertainty margin that we would expect. So it's a useful exercise to just get our eye in, and we're working our way to something more useful. If we go, click, please, David. Oh, yeah, so good relationship. I just quickly make the point about land surface temperature. Do we really care about land surface temperature? Why do we care about it? It's part of the picture. Sarah was talking about urban heat, about the climate, about all of the factors that mean people get heat stress or environment is overly hot and overly stressed. Land surface temperature is one of those components. Air temperature is probably a lot more relevant, but it's very hard to measure air temperature in a discrete way. So we use land surface temperature as something of a proxy. So a simple thing that we can do is take a satellite observation of a given day, land surface temperature. We can do some calculations and estimate what the air surface temperature was using Bureau of Meteorology data, and we can do analysis on that. So I've just done a very simple difference. You can see areas where the land surface is much cooler than the air temperature. They tend to be vegetated areas. So the mangroves up around St Kilda are very much cooler than the air temperature. And bare ground, of course, is quite a bit hotter than the air temperature. It's really just there to say there's a lot that we can do to correlate and analyze the two. It's what we need to do to get to something meaningful. Go one more slide, please, Dave. So I'll just take a slight step back to basics. What did we actually get from the satellites? What does that actually look like, and what can we learn from it? David's mentioned that Landsat and Hydrosat and Constellar, if you remember, are all around about in that 30-meter resolution. So that's a 30-meter by 30-meter pixel. And these are taken from panel A and panel B on the same day, almost at the same time. Let's just imagine that they're close enough to be comparable. Panel C is taken on a different day. It's actually taken on a cooler day, but I think you can see a difference. Panel C is far more detailed. We can see little features, and it also looks hotter. So we see our temperature scale there on the right-hand side of panel A, 25 to 55 degrees. Now they're all on the same scale. There's not much red on panel A, getting a little bit warmer on panel B, and we're getting, what looks to be significantly hotter on panel C. There's a lot we can learn from that. I won't go into any more detail than that today, but it's very interesting to see those differences in what would appear on paper to be the same resolution data. One more slide, please, David. These are those same snapshots, but now we're aggregated to the mesh block. And again, the same pattern is there. Panel C is showing us something quite different. It's hotter, and there are discrete differences. So this is all useful to know as we're trying to get an understanding of the way that the surface of Adelaide is behaving and how that will ultimately feed into our urban heat analysis. Next slide, please, Dave. Got really lucky, and I just wanted to show this. Sarah mentioned that issues to do with urban heat islands are about how hot they get, but it's also about how much they cool down. And so if things are not cooling down as much over the night time, then they're already preloaded with heat for the next day. So when we're in that heat wave scenario, things can get really hot. So a nighttime image, if the satellite provider can provide it, can do it, a nighttime image can be very telling to see how things are changing. And so ideally, we would want a day and a night image, but turns out that from the providers that we used, only Constellar was able to reliably provide us with a nighttime image. And we got a couple of nighttime images. We didn't always get a corresponding day and night. But I thought I'd just show that one. And if we had more time, or maybe in the discussion, we can talk about how the surfaces change. What was hot in the day, what is hot in the night, they're quite different. And it's very interesting. If we go one more slide, David. What else can we do from satellites? Sarah's aerial imagery snapshot, if you remember, had lots of blocks because they were captured at different times and all put together. So this beauty of a satellite like Landsat in particular, and Landsat is the best out of the ones that we considered in this regard, it has a very large swath. So we can capture all of Adelaide area of interest in one snapshot. We can also go back through time. There's a long catalogue of Landsat data. So this is 5 years of selected clear sky, hot days in summer, and then aggregated to mesh blocks. You know, this is how we're working now. So what does Adelaide look like on a hot day in summer as an average over the last 5 years? This is a useful baseline. We can work with this for change detection. We can work with this for an understanding of how the landscape is different, how there's hot spots, cool spots, etc. If we go one more slide, this is an example. Urban heat analysis is a very broad field, and it really depends on the drivers for the research, the data that's available, who's kind of prioritizing. Is this an environmental? Is this a human? Is this a design sort of thing? There are many different drivers, many different ways to cut the data. This is a very simple example using that same 5-year baseline. We do a simple sort of Z-score, and we can eliminate then the pixels in white are really those areas that are within one standard deviation of the mean. So from a statistical point of view, and this is just statistics, it's not the only way to deal with the data, but from a statistical point of view, just considering the land surface temperature, anything that's in white we would say is maybe normal. Anything that's in those blues is, you know, significantly cooler, and you can imagine anything that's in the reds is significantly hotter. It's one way to do it. And then we can do lots more with that. So really just a very small selection of results. That's really all. Just pointing out we've got lots of potential, and the satellite providers give us lots to work with, and there's still work to be done to understand how to best use that data in urban heat analysis. That's it, David. Over to you, I think.
So just going to compare these satellites that we've looked at already and in a bit of a summary, and also compare it with airborne. So what we've already seen is that with satellites, we can get high repeatability, days or even half days, if we can achieve that with something like Constellar, but typically out to weeks at the current point in time. With airborne, the repeatability is low, partly because of the cost and also the logistics of doing it. It can be months or even years. The spatial resolutions from space, we didn't focus on them a lot, but 30 meters is pretty standard. We can get down to reprocessed data at 10 and 20 meters. I'll show you an example shortly at 3.5 meters, but you'll see the limitations of that. And we get high resolution from airborne. So typically, you know, low temporal resolution, high spatial resolution. The time window, that is the time it takes to capture the whole city, is a few seconds, literally 20 or 30 seconds to capture the whole city from a satellite. Whereas with airborne, because of logistics and flying backwards and forwards and all of the other things that affect aircraft flights, this can be days, weeks, and we've even had examples of months of time delay between various parts of the image capture. And Sarah showed that a bit earlier. Closer to the ground, we're going to get probably better than 2 degrees, but around about 2 degrees. Up in space, the real errors are somewhere between 2 and 5 degrees. So what we see here is the trade-off between some of these things and cost. Now, we haven't shown you the actual costs here because they're partly because we used research data rates versus commercial data rates. But here's an indication of how it works. Landsat is free. native spatial resolution is 100 meters. By the time we get down to SAT view, we haven't talked about that much yet. SAT view, the relative cost setting a HydroSat Van Zel satellites at a relative cost of 1. These are 53 times more expensive than Van Zel. And we compare that with airborne, that's 72 times more expensive than Van Zel, but this is commercial rates, these are research rates. So take this with a grain of salt. And what we can see from that is that when we look at it graphically, that we see Landsat at 0 cost, and then as the relative cost increases, then the native resolution of the satellite improves. So SAT view and aerial are over here. So there's a pretty typical trade-off that we see with all satellite observations. So the current situation for summarising what we can do is that we can get sufficient spatial resolution to monitor areas, mesh blocks, or maybe larger units such as statistical area 1s or suburbs. The current frequency of collection, it's possible that if the constellations which make up these commercial arrangements are fully populated, that is, more satellites are launched into them, that we could get down to daily observations, and certainly Constellar is heading in that direction. But what we found was that cloud cover and the effects of atmosphere really restrict these. So to get to real-time daily observations is not possible at this point in time. There are some satellites, which I've mentioned one of before, which are at higher resolution spatially. This is SAT view, observed before our project started, nighttime image in 2023. This has a resolution of 3.5 meters to 5 meters, depending on which one we're looking at, but incredibly narrow swath width. So we can't cover the whole city in a single observation. So let me switch now to what can we do with this data, and Sarah's going to take us through on this particular section.
Thanks, David Michael. Yeah, so bringing it back to how satellite data can guide, or has the potential to guide urban greening action and start really combating or mitigating that urban heat island effect. So we've got anything from, as we mentioned, identifying those areas that are most impacted by urban heat and climate change. And that data that we've been looking at can provide an evidence base to inform strategies and influence policies about land management and development and vegetation management into the future. And then also identify areas for prioritising investment, so either through greening or infrastructure changes. And then also, as Michael mentioned, that ability to monitor over time Adelaide's change in urban heat and monitor that effectiveness of climate change mitigation strategies. I'll move to the next one. Thanks, David.
Sorry, I was having a cup of tea.
Cool, yeah. So as I mentioned, one of the options that we've got is looking at identifying areas most at risk of urban heat. And as part of this project, we undertook a small project, pilot project with GeoNeon, just for a small portion of Adelaide, using that Landsat imagery to look at areas that are most vulnerable to urban heat. So they went through a process with this small part of Adelaide, in this first instance, showing areas that tend to get hottest based on that satellite measurement of land surface temperature. So this is the first step. So if we go on to the next step, and using that mesh block level that Michael mentioned, this is a method that they applied to residential buildings. So the clear spots in this are non-residential areas. So this is applying that urban heat index to individual buildings and then aggregating it to that mesh block. So you start seeing the heat risk or exposure risk to residential areas within that 400-metre radius. So how much it would impact those residential buildings and people moving around their neighbourhoods. if we go on to the next one, and then when we combine that with the social vulnerability factors, you can see where people are most at risk, not only from that direct heat exposure, but also their risk in terms of social vulnerability. And as we mentioned before, just the people that don't quite have that ability to either adapt or have the capacity to mitigate their heat exposure. These are the people that are probably most at risk of that urban heat. And the next one. So as I mentioned, once we've identified the areas most at risk of urban heat and the people most at risk, we've got an analysis that was undertaken by DEW for us, which is the greening prioritisation analysis. So this is bringing together the tree canopy data that we captured back in 2022 with that Landsat urban heat intensity data, and combining it again with those social vulnerability factors such as age groups that are most vulnerable to urban heat, chronic health conditions, and socioeconomic disadvantage, all from the 2021 census. So bringing that together so we can identify these areas in red that are most in need of some sort of urban greening or cooling interventions. So these are areas that we'd and partners would be looking at for potential investment in the future. So we can really start planning ahead. And then also that next step is to monitor the change. So this is based on the 2023 Environmental Trend and Condition report card that DEW produced. And again, using a similar process to what Mike mentioned earlier, just taking that Landsat data again and comparing it. This was over 10 years of change. So comparing, was it 2014 to 2023, and just that overall change over those 10 years. So we can see that at the multiple scales we've got here, we've got the 30-metre resolution on the left and then the suburb resolution on the right. So at those multiple scales, we can start looking at those longer term trends of urban heat using that Landsat imagery. So yeah, in summary, what we've hopefully shown you today is that satellite data provides that vital evidence base to support policy and to help Adelaide be more cooler, greener, wilder and more climate resilient. So it's providing the evidence base. So we're able to define where there's areas and people at risk, and we're providing those really vital insights into the current status and impacts of urban heat and climate change. And then we can start prioritising where to act and where to invest, where it's most needed. And then after all that, we can monitor our progress and hopefully start seeing some positive changes. Oh, and yeah, just to finish off, just want to acknowledge everyone who's worked on this project. It's been a great project across multiple organisations. So we've had Mike and David from Flinders University, Fabrice from SmartSat CRC, and then within DW we've had James Cameron and Blair Pellegrino providing that technical advice from our perspective, and also just that that support from the different commercial companies that, as Michael mentioned, they're new startups in terms of satellite companies. So it was great that they were able to share their data and experience and support this project. But thank you, everyone.
Fantastic. Thank you so much, team. And yeah, great to see such a collaborative project across corporate, universities, government coming together as well, and know that seeing the benefits of that as well is fantastic. Great work across Adelaide. It's a good place to make that kind of thing happen as well. So really good to see that model at work. We've got a couple of questions in here. Some people seem to keep dropping out and coming back in, so I hope you're not missing out, people that seem to be doing that. This is from Michael. Hi, Flinders gang. Question: other methods for heat island effect, heat island index seem to compare city temperatures to non-urban baseline, example the Adelaide Hills. Was there any consideration for this type of baseline?
Yeah, Yeah, go for it,
Who
David.
wants to jump in? Do
Well,
you want
David.
to just stop sharing your presentation and then people can see your faces a little bit more clearly for the questions?
Okay.
Perfect.
Mike might have something to say about this. It's a matter of scale. Do we look at a city and compare it with its surroundings? That's what the question is proposing. And if we did do that, then it would come down to very much the time of year, because bare soil in our agricultural areas is hotter in summer, cooler in winter with crops on it. So that's one of the issues. But I mean, when we look at the urban heat island literature, you know, it's fast moved into smaller units than whole cities being hotter or cooler than their environments, and looking at sections of cities. So, you know, right down to the pixel or to the mesh block or to the suburb. And I guess some of these things come down to what are the management units that are sensible to work with, but also the resolution, the resolution of our satellites, what can they reliably be used for? And so if we work at the pixel level, we see quite a lot of noise, and that's why aggregating to these bigger units is better. So it also comes down to statistics, you know, was it Disraeli and Dan Lyons and statistics and all of that? So you can manipulate this data any way you like by changing different spatial extents, and you'll get different statistics from it. Mike, do you want to add to that?
I think that the field is very open. The urban heat analysis field is very open, and there are different approaches that are well published, but they are different, and you will get a subtly or dramatically different result depending on the exact situation. I believe that the DEW imagery that Sarah showed used a vegetation mean. I used a straight land surface temperature mean. The weakness of my approach was the temperature gradient over the Adelaide area of interest we know is quite large. It is just genuinely cooler in the south and warmer in the north. So if you're going to use a mean, a single mean, what, you know, that may not be representative. I put the image up as a topic for discussion, so I'm glad that it has triggered that, and it's one way to do it. There are many, and it would require some research and also reality checks of what data is available and appropriate to use to come out with the best method. And then we should use that method going forward so that we've got some comparison options.
Yeah, because definitely that would be going forwards if there was that agreed upon
kind of the scope of work that we were working at was evaluation of satellite data, what that looks like, what our findings were in terms of how useful it was. The analysis of urban heat is almost another project. Because,
correct.
There's lots of different things to consider. Yeah.
That's right. It's like what we do with the data next. Is the next project. Yeah.
Absolutely.
Some other interesting questions here as well. What exactly are the impacts of the atmosphere on data collection from satellites? I thought that was a good question.
Well, as I said earlier, the atmosphere affects everything, except possibly up in the microwave part of the spectrum, but even there are some issues. But in the visible and the thermal infrared part of the spectrum, we get atmospheric scattering, which causes all kinds of effects which have to be taken into account. So the normal approach is with thermal data is to use at least two spectral bands, two thermal bands, and do what's called a split window comparison, and known ground points whose temperature is known, and then coefficients are worked out for that particular sensor. But then the next time the satellite flies over, the atmosphere is subtly changed again, so that has to be corrected for, and there's some modelling work in that, and that's what gives rise to uncertainty. And Mike can tell you about the uncertainty in a number of products, but maybe in Landsat and Hydrosat would be interesting to talk about.
So we saw a number, and I didn't show any slides because we were just pushed for time, and it's kind of complicated. But we saw several examples of clear sky. I mean, obviously, atmosphere The major atmospheric interrupter is cloud. So let's just say that if it's a cloudy day, we really don't have much to work with. If it's a clear sky day, it was very interesting to see the differences in uncertainty. When I say uncertainty, there's a number of layers and a number of analysis techniques that we can use to drill into the data. Just because it's shown in the pixel, we want to know, well, where's it from? What do we know about it? And we call that uncertainty. It was fascinating to see on clear sky, hot days, levels of uncertainty that were really confusing. And so we had to make some sort of scientific judgments really to think, is this useful? Like, where do we draw our sort of boundaries to cut down the effects of this? And it was a bit dynamic. I thought that would be much more static. We understand emissivity, we understand solar radiation, we understand that a similar land surface will react in a similar way, but it is problematic. So I don't know if that answers the question, other than saying the atmosphere does introduce uncertainty and some limitations into satellite data. And the major weak point is cloudy days. And there's a lot of cloudy days, even in Adelaide, even in summer.
Yeah. No, really good to be aware of that. And I think that same question asker, Savani, she's a recently graduate, a geography graduate, and is wondering if there's any opportunities to get involved with future research. So we'll be sure to share emails and contacts afterwards so she can keep in touch, because I'm sure there'll probably be ongoing things to contribute to. Bianca's got a question here. What is the capacity to use this information freely? This one might be for you, Sarah. Can I find overlay data to match this to a different suburb or area? How's the data available for people at the moment?
I guess it depends on which data you're looking to use. So all the data that was captured by Green Adelaide and partners back in 2022, so tree canopy, that aerial thermal imagery, that's available to view on the Urban Heat Tree Mapping Viewer. So if you just Google that, it'll pop up. And most of that data is available to download through Data SA. But if we're looking for satellite imagery, probably Michael and David are best ones to ask about that. The commercial ones, I think, were, they were paid for, but Landsat imagery is freely available, but I'm not entirely sure, I guess, how that would work.
Yeah, the Landsat data is freely available, and it's relatively straightforward and well mapped out how to work with it, but it is a technical process. I think it would be ideal to publish this kind of data in a more processed level, in an urban heat relevant sense, and maybe that's something that Green Adelaide and co will work towards. I would love to see that, but at the moment Landsat is available, and if you're interested, reach out. I can give you some pointers there, and it's not that hard.
Okay, right.
Let me jump in here on the commercial satellites. Obviously, they're putting the satellites in the sky to earn some dollars. So, and generally those dollars are more expensive as the resolution, temporal or spatial resolution increases. So, yes, their data is going up into image stacks, but you have to buy a subscription process to that to get hold of it. And if we're looking at a whole city, you would think that would be a government-led sort of proposal.
Sure. Which this next question kind of bleeds into that one, in terms of noting that there are from Stefan Kardivelik, noting that there are several satellite-based solutions available, as well as airborne data collection, which we've been repeating every few years. What kind of monitoring regime do you think we should be investing in, and do you know anything about that kind of regular cost for those, if we were to kind of keep doing it at the level that you're talking about?
I think, as Michael said before, that I think just having Landsat there as that workhorse, it's been, I think the current satellite's 10 years old, so we've got that consistent data that we could potentially backdate some of that analysis to. So I think in terms of as a baseline monitoring, Landsat will be providing that sort of service. But that's something that Green Adelaide and partners really will be investigating, I guess, sort of how do we go beyond that? Do we start looking at prioritising areas for further investigation with the high resolution satellites, or are we happy with that long-term monitoring with lower resolution Landsat? That's definitely something to be investigated. David?
David?
Let me add that this scene is changing rapidly. So as Landsat is free, that's wonderful. But there are the number of players in the commercial space will force the dollars per square kilometre down. That's for sure. We've just put in a proposal to the Chinese Academy of Sciences to use one of their satellites, which at the moment is free. Well, we think it's free. We're not entirely sure, with a much higher resolution and swath extent than what we've seen already. And so these are the changes that are occurring. But for these private concerns, they're going to get to a point where they say, we're not going to release the data without getting some return. So we'll leave it at that, I think.
Yes, complicated space there as well. So, so Sarah, what you're saying, because there's just an interest kind of more than a question from Brad Mann at Tea Tree Gully around it, how it would be interesting to see what impact the tree removals undertaken over the past few years from the giant pine scale outbreak, for example, in Tea Tree Gully has had. And so, whether those focused on, rather than doing backdating the whole of the city, whether there could be smaller focus areas and that type of thing as well.
Yeah, that's something I've been starting to investigate, is just areas where we could start using a few test cases of how effective is this to monitor like known change, like tree removal and interventions. Like one of the examples, I've been talking to someone at Renewal SA about areas where light coloured roofs have been mandated. Can we pick that up with satellite imagery? So yeah, it's going to be interesting to test those areas, so to see if we can start seeing change.
Yeah, definitely. And just a clarification question, I think someone may have answered, Alicia, but is the Green Adelaide due greening prioritization analysis, is that using the 2022 data? Is that right?
Yeah,
Sarah?
Yeah. So 2022 data together with Landsat imagery from about the same time.
As well as Landsat. Yeah. Yes. Fantastic. Excellent. Well, I think we've got through most of them. There might be, is it available? Have we made this public yet, Sarah? Soon?
Not yet. It's just going through external review. So we've got that's in process. Hopefully the plan is to upload that to the Urban Heat tree mapping viewer in the next few months, hopefully. But we'll see how that goes. That process goes.
Yeah, you'll be the first to know, Alicia. And there's one final one here looking at residuals. So in the slides comparing in situ measurements with Landsat LST retrieval, surfaces such as roads show smaller residuals while water and grass show larger residuals. Is there any reason for these differences? Is that a quick question to answer, or should we follow up that person afterwards?
Well, they're highly variable.
Highly variable. Yes, that's. I was predicting that.
I think it's an interesting discussion. Let's have an offline discussion about that if we can, through email or whatever.
Yeah, no worries. We'll link you up there with Sharu, I think her name is. Thanks so much for all your questions today. And if any of them have slipped through, we'll be sure to follow them up afterwards as well. So thank you to Sarah, David and Michael, and to all of you that have joined us live or be watching later on YouTube. We'll be sure to update you with the changes in this area as we go. As everyone has said, it's quite an evolving space. And we'll send out an email. And just to remind you that our next webinar is coming up on the 16th of June, and this one is going to be all about discovering the Atlas of Living Australia, where viewers will learn how to access and use the incredibly rich biodiversity data available through the platform, and we've got a lot of interest around that one already. So we'll send you more information on this session and how to register with a link of this current recording as well. So we hope you can join us at the next one or jump into the backlog that we have on our YouTube channel. So there's lots of great webinars there that you can listen to on your commute home. So thank you all for joining us, and it's 5 o'clock. Have a great evening.
All right. Thanks a lot.
Thanks,
Thanks,
Christy.
everyone.
Thanks, everyone.